Example 3, analyzing the motion of a spring. An object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t equals 0. You can see the figure here and note that the downward direction is positive. Its position at time t is s, which is equal to f of t, which is equal to 4 times the cosine of t. So since we know that this is the position function, what we want to be able to do is find the velocity and the acceleration. So again, here what we're going to do is we're going to find the velocity and acceleration at time t and use them to analyze the motion of the object. So first thing we're going to do is find the velocity, and then we're going to find the acceleration. So for step 1, let's recall that the velocity is equal to ds over dt. Okay? And so what that means is we want to find the derivative with respect to t of 4 times the cosine of t. Okay, so again, recall that we can factor out the constant 4 and multiply it by the derivative with respect to t of the cosine of t. And so that's equal to negative 4 times the sine of t, because we know that the derivative of the cosine of t is going to be negative sine of t. Okay, so now we're going to find the acceleration. So remember, the acceleration is equal to dv over dt. So that means that we want to find the derivative with respect to t of the velocity, which is negative 4 times the sine of t. So again, if we factor out the constant negative 4, this is negative 4 times the derivative with respect to t of the sine of t. And so therefore this becomes negative 4 times the derivative of the sine of t, which is the cosine of t. So here is the velocity function. Okay, here is the acceleration function. And we know that this represents the position function. So now let's go ahead and graph this all on the same graph using Desmos. So we have the 4 times the cosine. We're going to use x as the variable. And then we're going to have negative 4 times the sine of x. And then our acceleration is going to be negative 4 times the cosine of x. Okay, so let's go ahead and copy this. Okay, so now let's label this. Okay, so we know that our first graph that we graphed was the function 4 times the cosine of t. So we know that the position function is equal to 4 times the cosine of t. And then we can see that the velocity function is equal to negative 4 sine of t. And the acceleration function is equal to negative 4 times the cosine of t. Okay, so let's evaluate what's happening here. Okay, so what it's saying here is that the object oscillates from the lowest point, s is equal to 4 centimeters. So up here, this is the lowest point with the position function. and it's oscillating to the highest point where it comes down here at -4. And then it's going back up to +4. So it's oscillating. So therefore, the period of the oscillation is 2 pi, since it's cosine of t, so the period of cosine of t is 2 pi. Now the speed is represented by the velocity. And the velocity, if you take the absolute value of the velocity, that means if you take the absolute value of this function, the absolute value of -4 is 4, and therefore it's 4 times the absolute value of sine t. So it says which is greatest, okay, when the absolute value of sine of t is equal to 1. That is when the cosine of t is equal to 0. Okay, so if you look here, wherever it's t, wherever cosine of t is equal to 0, there's the horizontal. Okay, then it comes back up here, right? Okay, and then again, if you come back here and you go back up, then down here again we can see that there's the cosine of t, which is equal to 0, and then there's the other horizontal. So the object moves fastest as it passes through its equilibrium position where s is equal to 0. Its speed is 0 when sine of t is equal to 0, and that is at the high and low points. Now if you take a look at the acceleration function here, where a is equal to -4 times the cosine of t, wherever it's equal to 0 is when s is also equal to 0 here. It has a greatest magnitude at the high and low points.